Okay, my research paper was about the past, present, and future of logic gates. And I did it alongside my mentor Nirvana, who goes to the University of British Columbia. She's a graduate student. And so this is some context that you need in order to understand my research. So logic gates are digital circuits that perform logical operations on binary inputs and produce binary outputs. And they're used in like pretty much everything, like especially device that you're using, like your laptop, your computer, your phone. That all uses logic gates and depends on it. And if we didn't have logic gates today, our world would be totally different. And on the side, this image here are some examples of logic gates. And like if you're into coding, like you could probably understand it's easy. Like the AND gate is, or like the OR gate is similar to coding, like the coding and or. It's something that many languages have. And so current logic gates are digital, which aren't suited for the future needs of the world because computers demand hardware that's efficient and smaller. Like sometimes you might see a program that needs like, let's say 100 gigabytes of storage, and those chips take up a lot of space in your computer. So computers are slowly kind of getting bulkier as they once were when they were first created. And because of this demand, researchers have been finding applications for logic gates in other fields other than computing. And specifically, these applications have been found in genetics, chemistry, and neuroscience. So logic gates are significant because of how heavily around them today, as I said earlier. And the reason why I'm writing my research paper on the future of logic gates is because most research papers don't really like talk about the future. Like they talk about how these new logic gates work, and all information in my paper comes from like credible resources, like previous research papers. So I'm going to start with an application of genetic logic gates, and this is like a really, really new field, very recent. So there's not many applications for this, and they're used for genetic regulation by controlling the flow of DNA using a device that's similar to a transistor. And if you don't know what a transistor is, this is also used in a lot of computers, and they control the flow of current. So it's similar in the fact that it's like the flow of RNA and the flow of current. And this method has only been experimented with in bacteriophages. And then the second field is chemistry. So chemical logic gates have been used to detect diseases, which enables early diagnosis and treatment. And its detection occurs through like logic systems distinguishing between disease cells by examining 2 or 3 different cell markers. And this has only been tested in cancer, and this was like a very successful experiment, and it was specifically tested in like rats or mice with cancer, and then they were cured in like 60 days. And the image below, I'm sorry, the image below is an AND gate. So, so sodium and hydrogen are detected in this molecule, which is which releases a change in fluorescence, which represents like the detection of like the pathogen, the disease, whatever is like being detected. And the final application is in neurology, is neuristors. And unlike molecular logic gates that haven't really been used because they can't handle high voltages, because they can handle a maximum voltage of zero point 0.3 volts, which means they can do like nothing. Because most computers use like 12 volts, or like chargers use like 5 volts. So they're not very useful. But they have been used to create every digital circuit, and they have a lot of potential to replace them and make every computer smaller and faster. So this is something that was made with neuristor-based digital circuits, artificial neural networks, and they were created to speed up processing time in computers, and they were inspired by the human brain and are 7 times more efficient because of their higher fault tolerance. And they have a lot of potential applications such as image recognition, marketing, forecasting. So they are very applicable to our lives today in fields outside of computing. So like this is kind of like a summary because all 3 of them have their own respective disadvantages, which is why they aren't being widely implemented. So the first part is genetic logic gates. They have many ethical issues because the effect of regulating DNA in this manner is unknown, because this might have a lot of environmental or species related effects. And molecular logic gates aren't easily scalable because molecules and compounds they break down over time. So replacing these medical devices happens often. It's going to increase the cost. so they're not really advantageous over traditional devices that are being used today. And resistors cannot handle high voltages, as I said earlier. 0.3 volts is not good enough for really anything. But all of them have like a lot of aspects that make them better than traditional digital circuits. So what my mentor and I thought was that future researchers should focus on solving all of these issues. Hence, ethical issues should be resolved before furthering research on genetic logic gates in order to prevent any future problems. And new molecules should be utilized, and new research needs to be used at higher voltages if that is possible. Well, thank you.